Now, when we're sketching the graphs of rational functions, and this includes reciprocal functions, we need three things. We need the asymptotes, we need the x and y intercepts, and the invariant points, which must be in reference to the original function if we're talking about the reciprocal function. So, when we're graphing rational functions, it is simpler to categorize them into reciprocals and then non-reciprocal rational functions. So, when it comes to graphing reciprocal functions, we're going to do it in light of the original function. So, f at x is equal to x squared represents the original function, and g at x equals 1 over x squared represents the reciprocal of f at x. And so the process is fairly simple, although it can look complicated. But if you follow this, it should help you consistently solve these problems or sketch graphs of reciprocals. So first we're going to find the horizontal and vertical asymptotes and plot them. Then we're going to find the x and y intercepts of the reciprocal function. And then we're going to find the invariant points with respect to, of course, the original function. And then after that, and I kind of put it as a secondary note because you kind of do it at the same time, then we're going to find the end behaviors around the asymptotes once we have these plots pointed. So we've drawn f at x is equal to x squared graph over here, and what we're going to do is, like we suggested, we're going to find the horizontal and vertical asymptotes of the reciprocal function here. We know that the vertical asymptote is that which makes the denominator 0, which in this case is going to have to be at x equals 0. So we're going to have a vertical asymptote at x equals 0, and I will draw a purple line through it here. At the same time, we're going to have the horizontal asymptote, which, since the numerator has a smaller degree than the numerator has a degree of 0, the denominator a degree of 2, then that's going to have a horizontal asymptote at y equals 0. So in pink, it'll go right across the x-axis over here. Now for part 2, to find the x and y axis, we're going to simply sub in for g at x. Let's say if I want to solve the y-axis first, I'll sub in 0, but the problem is you cannot put 0 in the denominator. It is undefined, so we're going to write that it has no y-intercept. And then for the x-intercept, we're going to do the same thing. We're going to put 0 at g at x over y equals x squared, but the problem is when I try and solve for x, it too would have no x-intercept because you cannot solve for x. The x simply disappears when you multiply by 0, so we're going to write here no x-intercept. Now reciprocal functions always have invariant points at x and 1 and x and -1, and the reason for that is because if you think about it, if the f at x is equal to -1 and my reciprocal is 1 over f at x, and I go 1 over -1, that is still going to equal to -1, so they're going to share that point. And the same is true for 1, that if I have f at x is equal to 1, and then I'm saying that the reciprocal, and I'll just write the g at x here for the reciprocal, I didn't write it the first time, I'll write it now, the g at x is equal to 1 over f at x, well, 1 over the value of 1 is equal to 1 anyway, so they're always going to share the values of 1 and -1. However, in this case, when we look at this graph, your original function doesn't have a value at -1. Now, since there are no other points to consider and we cannot cross the purple or pink lines, then the end behaviors are not really necessary to find because we know that they're just going to approach the asymptotes. So your reciprocal graph will really just end up looking, well, like this. And it couldn't be anything else since it has to come from those points. But this is not always going to be the case. Let's look at another example. Now let's say we're graphing the reciprocal of f at x is equal to x squared minus x minus 2. And that would be the g at x over here. We're going to do so in light of this one. So like we did previously, and here's the graph of f at x in black here, we're going to get the vertical asymptotes and the horizontal asymptote. Now, in this case, we're going to factor the quadratic over here. So x squared minus x minus 2. When we factor this, we end up getting, and you could do this several ways. I'm kind of skipping this step here, but we end up getting x minus 2 and x plus 1. So that means that there's a vertical asymptote, and I'm going to write this here. Vertical asymptote at x equals 2 and x equals negative 1. And then for a horizontal asymptote, since the numerator has a degree that is less than the denominator, then we know that there's a horizontal asymptote at y equals 0. So now we've got the asymptotes, we're going to plot those. So I'm going to, let's say I get the x-intercept. I'm going to plug in 0 for the y. And if I were to isolate this here, I would see that actually there is no x-intercept. Now the reason there's no x-intercept, because imagine I try and isolate for x here and I cross multiply it with 0. Well, all those x's are going to disappear anyway. So there is no x-intercept. Now let's do the same thing for the y. And for the y, we're going to set the x to 0. So we're going to go g at x is equal to 1 over, and that's going to be 0 squared minus 0 minus 2. And that's just going to give us a value of negative 1 over negative 2, which is the same thing as saying negative 1 over 2. And so what I did here was I plotted that y-intercept at 0 and negative 1 over 2. The last thing we're going to do is we're going to plot the invariant points. And since it is a quadratic, remember that there's always invariant points at 1 and negative 1. The tricky part is that the ones, if we look at where y equals 1, there's 2 x values for that. So we're going to put for 1 twice, and as well for negative 1, there's also 2 x values for that as well. So we're going to put for negative 1, we're going to put that twice. And so what we're going to do is we're going to plug in 1 for y and then isolate for x. And let's see what we end up getting. After I factor this equation, when setting it at 1, I get a value of negative 1.3 and 2.3. So I go and I plug in those values over here, and that would be negative 1.3 in 1 and 2.3 in 1. And then I'm going to do the same thing with the negative 1. So I plugged in the negative values, did the quadratic formula, and I got these remaining x variables for the invariant points. And so now from the invariant points, we're going to plot these. Once you've plotted the invariant points and you have the intercept, you could just follow the asymptote line. So what I mean by that is, remember that since this graph is going to approach the asymptotes but never hit them, well, that means that if I look at this point over here, so I'll highlight this, that it's going to approach the green line but never actually reach it. And from that same point, it'll actually approach the red line but never actually reach it. And the same is going to be for the other side, where from this point, it'll approach the green line upwards but never actually reach it, and approach the red line but never actually reach it. And it has to go this way because it wouldn't be able to go the other way without crossing that asymptote, the green one. So the asymptotes really just kind of confine where your graph goes. And from the intercept here, I know that it's going to start from this point and then go to the next point because it is a point on the graph, and then once again follow the asymptote lines just like this. and from this point to the next point, and then follow the asymptote line. So you don't necessarily have to calculate for the end behaviors, but you could technically do it this way, and it should work out. The end behaviors just kind of give you more numerical reassurance. Now for the second category, we have just a regular rational function. It's not a reciprocal, but we're going to approach it the same way. We're going to attempt to get the vertical asymptotes and the horizontal asymptotes. And before we do that, we're going to factor, because we know now that you can have points of discontinuity or holes in the graph. So what we have now may not actually be what's left over when this function is simplified. So let's factor the numerator and the denominator. So once we factor this, we get the following for the numerator and the following for the denominator. We can see that the x plus 3's cancel out, and that's significant because if we go back in last video on discontinuities, whatever cancels from the numerator and the denominator, that tells us that there's a hole or a point of discontinuity at x plus 3. So the real function that we're actually working with is x minus 2 over x minus 1. Now when we look at the vertical asymptote, whatever makes the denominator 0, that is the vertical asymptote. In this case, a value of x equals 1 would make that 0. So we're going to write there's a vertical asymptote at x equals 1. For the horizontal asymptote, because they're the same degree, both a degree of 1, it's simply just the ratio of the leading coefficients. So if we go x over x, that's going to give us 1. So there's a horizontal asymptote at y equals 1. So we have our horizontal asymptote, our vertical asymptote, and we know that there is a hole. What we're then going to get are the x and y intercepts of our function. Now, of course, this is going to be the simplified functions. So I plotted the vertical and horizontal asymptotes here. The vertical's in blue and the horizontal's in green. And then what I'm going to do is I'm going to plot the intercepts. So we said that there was an x-intercept at 2. So we know we're going to draw a little point at 2 here, x equals 2. And then there's a y-intercept at 2 as well. So we're going to draw a point here. Now, there's also a point of discontinuity. And we figured out that the point of discontinuity of the hole is at, it was at -3. Now that's the x coordinate of the hole, but we need the y coordinate as well. So let's quickly plug that back into our equation, and we're going to get the y coordinate of the hole. So by plugging in the x value into the equation, we end up getting a y value of about -5 over -4. Or if we're thinking about a decimal, that's positive 1.25. So at about 1.25, so if we use these grid lines here, so it's roughly about at 3, so -1, 2, 3, and 1.25, so a little bit above, we're going to draw a circle, a blank circle, because remember that that point is not included. And so from then the intercepts, we're going to follow the asymptote. So we're going to go upwards, approaching the vertical asymptote, and then downwards, approaching the horizontal asymptote. Of course, skipping or not contacting the other asymptote. And then from this way, from the other intercept, we're going to do the same thing. We're going to go towards the horizontal asymptote and then down towards the vertical asymptote. And this provides the graph for our rational expression.